Well, congrats everyone, we made it to our final episode on our series of videos on trigonometry. I know we didn't quite cover everything in these 7 videos, but hopefully you've had a basic introduction to all the aspects of trig that you'd normally learn before calculus. By this point in the series, if everything's resonated with you, you'd probably understand at least how to do any trig problem that would appear on a high school math test. And that's good enough, considering the scale and mission of these videos. We're trying to improve proficiency in high school math so that you can all go further in your applications of it, remember? And for those of you who won't get past pre-calc before college, I think we've done it. But, of course, there's a little more to trig than what we just covered, so consider this somewhat of an extra episode. You won't need it outside of certain classes, but it's still common and interesting enough that I wanted to cover it. Welcome to Trigonometry and Calculus. One of the fundamental concepts of calculus is that you can measure the instantaneous slope of a line at a given point. Think of this as the rate at which the function is changing at one specific point. This is called a derivative, and we represent it with dy over dx or f prime of x. If the function is increasing at the point measured, the derivative is positive. If the function is decreasing at the point measured, the derivative is negative. Just as individual points on a function have a derivative represented by a constant number, entire functions have derivatives represented by another function. This all sounds a little weird in the abstract, so let's put it into action with a specific example. Let's find the derivative of the function x squared plus 5x plus 7. Now, there are many ways to find a function's derivative. The way people are first introduced to it is through a big formula I won't get too far into. In this formula, f of x represents the given function and h represents a number very close to 0. You might recognize that this formula is similar to the formula for slope. Since we're taking the slope of the function using 2 points separated by a distance of h, the first formula is just a specified version of the second formula. y1 is f of x. y2, h points away, is f of x plus h. The difference in x values between the points is just h. So this way gets us the derivative of the function at a certain point, but it's through a pretty rigorous process I don't want to spend too much time on. What your calc teacher won't tell you until you're a little ways into the class is that you can find the derivative of this function really easily with something called the power rule. The power rule states that the derivative of x to the power of n is equal to nx to the power of n minus 1. You multiply every x value by its exponent, then raise it to a power 1 less than the one it had before. Through this system, the derivative of x squared is 2x to the first, or 2x. The derivative of 5x to the first is 1 times 5x to the 0, or 5, and the constant value 7 just becomes 0. Think of it this way. Derivatives measure slope, and the slope of the line y equals 7 is 0. Or, mathematically speaking, 7 is equal to 7x to the 0, and applying the power rule gives us 0x to the power of negative 1, or 0. We can take all of these singular derivatives and add them together to form the derivative of our function, 2x plus 5. So that's what a derivative is and how they work. Are your heads spinning? No? Good. Now let's get into deriving sine, cosine, and tangent. The rules you'll be taught to memorize in calculus are that the derivative of sine of x is cosine of x, the derivative of cosine of x is negative sine of x, and the derivative of tangent of x is secant squared of x. But here at putting trigonometry back together, wow, that really doesn't roll off the tongue well. Here in these videos, we don't settle for memorization, so I'll explain how each of these derivatives work. Now, I could do this mathematically, but that requires a really long set of complicated trig identities we haven't worked with yet. Getting you from the Pythagorean identities to the things you need to know to prove that the derivative of sine is cosine would be a lot. Seriously, there are semester-long courses dedicated to that, and I can't cram that into one video. Trust me, I tried. God, did I try. But I scrapped all of that because it confused me and I don't want it to confuse you, so let's look at some graphs. Alright, let's compare this graph of sine of x to the graph of cosine of x. If we're going to take the derivative of sine, we'll have to know when it's increasing, when it's decreasing, and when it reaches local extrema, high and low points. First, notice where sine is increasing, from 0 to pi over 2, and then again from 3 pi over 2 to 2 pi. You'll remember that this is where the derivative of sine would be positive. Also, sine is decreasing from pi over 2 to 3 pi over 2, so this is where the derivative would be negative. Over a period, cosine is positive and negative at these exact intervals. Let's see what other clues we can find. Sine reaches a local maximum, or highest point, at pi over 2, and a local minimum, or lowest point, at 3 pi over 2. An important thing to notice about these points is that they have an instantaneous slope, or derivative, of 0. Right at these points, the function isn't increasing or decreasing at all. So, cosine should cross the x-axis or be graphed at 0 at these points. But that's not all. At pi over 2, the slope of sine goes from positive or increasing to negative or decreasing, so cosine should cross the x-axis from positive to negative there. The reverse is true for 3 pi over 2. And if we look at our cosine graph, it all matches up. All the key graphical signs of cosine being the derivative of sine have been met. Wasn't that easy? I'd love to take the time to explain the other two derivatives to you, but I'm trying to make this brief, so here are some side-by-side graphs of the cosine graph and the negative sine graph, as well as the tangent graph and the secant squared graph. See if you can find all the similarities that make one the derivative of the other. So finally, to end this series off, let's take the derivative of an equation involving trig functions. There are lots of rules I didn't tell you about that make it easier to derive equations more complex than this one, but for now, see if you can do this one. F of x equals 6x to the fourth plus 4x to the sixth plus sine of x minus cosine of x plus 570,936,412.
It's almost the Homestuck number.
Cool. I just hit random numbers and tried to make it diverse. That should be easy enough. Pause the video now and play it when you've got an answer. Ready? Let's go. First, let's address the elephant in the room, 570,936,412. Since it's a constant, a line with that slope would just be flat and really high up on the y-axis, its derivative is 0 and we can just ignore it. Yay! There are two values here that we can use the power rule on pretty directly. By multiplying their coefficients by their exponents and lowering their exponents by 1, we get that the derivative of 6x to the fourth is 24x to the third, and the derivative of 4x to the sixth is 24x to the fifth. Next, we remember that the derivative of sine is cosine and that the derivative of cosine is negative sine. Using this, we get our final answer, 24x cubed plus 24x to the fifth plus cosine of x plus sine of x. And that concludes the final episode of Putting Trigonometry Back Together. I know Kinry and I didn't cover everything in this series, but we really did our best to give you a surface-level introduction to all the major parts of trig. We really hoped you learned something from this series, whether it was the level of geometry or calculus, and we hope that now trigonometry is a little less broken.